Right, this unit is over thermochemistry. So for thermochemistry, STP means standard temperature and pressure, and STP conditions would be 25 degrees Celsius or 298 K. We're going to stick with Celsius for this, and pressure is 1 atmosphere. Okay, all reactions either release or absorb energy, and abbreviate energy with a capital E. Heat energy is referred to as enthalpy. So the delta H, the triangle, and the H, that's enthalpy. Your units are going to be joules or kilojoules, and we can only measure the change in enthalpy. That's why we put a triangle here. This means change. And so when you're finding change, you're going to take your final and subtract your initial. Okay, so here's the different types of energy. Thermal energy, this is what we're going to do now. Mechanical energy, it's physics. Nuclear energy, we did that unit 4. Chemical energy, any kind of reaction. Electrical energy, electromagnetic energy, these are kind of physics. So right now we're going to focus on thermal energy. You might need to know some of these examples for the test though. All right, you need to draw these graphs. This first graph is an exothermic reaction. If you look at where the energy of the reactants start compared to where the energy of the products end up, do you see how there's less energy? That means we've released energy. So all exothermic reactions are going to release energy. And you form bonds when you release energy. So anytime you form bonds, exothermic reaction. Okay? Down here an endothermic reaction, and if you look, the energy of the products is a lot lower than the energy of the reactants is a lot lower than the energy of the products. So for endothermic reactions, you absorb energy, and here you're breaking bonds. So on a test, I could give you a picture of these graphs, and you should be able to tell me, oh, that's an exothermic graph or endothermic graph. All right, so when you think about if you're forming bonds or breaking bonds, you got to think about the intermolecular forces. What's happening? So if you have an ice cube and it's a solid, right? The molecules are very close together. You're going to a liquid, they're getting a little farther apart. So you've broken bonds. That means this is an endothermic process because we've broken bonds. Here, you have a liquid, the molecules are far apart. You go to a solid, you're freezing, they get closer together. You're forming bonds, so this would be exothermic reaction. So here's a graph that kind of illustrates that better, which you need to draw in your notebook. So on your y-axis you have temperature, and on the x-axis you have heat energy. So as you add energy and temperature, you're warming up, you're breaking bonds, breaking bonds, breaking bonds. So on this side of the graph, these are all exothermic phase changes. And here, as you go backwards, you cool, you get closer together, closer together. These are all I switched them. These are exo, sorry. These are endo. Yikes. All right, specific heat. So specific heat is, let's label these. This is Q. This is your energy, and it's measured in joules. M is mass. Okay, grams. C, that's specific heat. This is how much energy it takes to raise the substance, whatever substance you have, 1 gram of the substance by 1 degree Celsius. So it's basically how much heat can this substance absorb before the temperature changes. And here is your temp change. And remember, when you find a change in anything, it's always going to be your final temperature minus your initial temperature. So how much heat is required to warm 400 grams of water from 20 degrees Celsius to 50 degrees Celsius. So we're just going to plug everything into this equation. Okay, we don't know Q, right? How much heat, that's what we're trying to find. Our mass is 400 grams. Now, the specific heat either has to be given to you or you look it up on a table. For water, it's 4.184, and water you have to memorize because you use it so often. So the specific heat of water is 4.184, and then it's always our final temperature minus our initial, so it went from 20 degrees Celsius to 50 degrees Celsius. All right, and that will give you 50,208 joules. And because Q is positive, the sign of Q is positive, this means that this was an endothermic reaction. If it had been negative, it would have been exothermic. All right, Hess's law. Hess's law says that if you add two or more thermochemical reactions to give a final reaction, then you can also add your heats of reaction to give the final heat of reaction. So now we're looking at enthalpy. What was the overall change in energy of these reactions? So we're going to start out here. This is our final equation. This is what we're going to end up with. And we know all these little pieces. This is what we know. So we need to manipulate these in order to get this final equation. So you just match everything up. I'm going to start with 2 and 2. I'm going to find it here. Well, here's N2, but I only have 1, so I need to multiply this by 2. If I do that, I have to multiply my delta H by 2. Okay? Then I'm going to go back to my equation. I have 5 O2s. Okay, well, I've got some O2 here. I've got some O2 here. I don't really know what to do, so I'm going to save that one for last, and hopefully it'll just kind of work out on its own. Then I've got 2 N2O5s on the product side. And here in the second equation, I have N2O5, but it's on the wrong side. So what I'm going to do is I'm going to flip this second equation. And when I do that, I have to change the sign of my delta H and make it positive. So I'm going to rewrite all these equations and see what I can cancel out. Okay, I said I was going to flip this one. Now I'm noticing I've got 2 NO5s here. I only have 1 here, so I need to go back and multiply this whole thing by 4. I'm sorry, by 2. So that will give me 4, 2, 2. There, now it matches. And I said I was going to multiply this one by 2. So 6, 2, and 4. Okay, so whatever I did to these, I need to do to these. So this one was still 571.6. This one, I flipped it and I multiplied it by 2. So that gives me 147.4. This one, I just multiplied it by 2. So that gives me 696.4. Okay. So let's see if this cancels out. So I've got, you look at the arrows. They can cancel out on either side of the arrows. So let's see. I have 4 NO3s here. I have 4 HNO3s here. Okay, I'm not able to cancel out my water. They're on the same side, and I don't have any water in my final equation. So I need to flip this. I need to flip this equation. Why is it not letting me erase? Why can't I erase that? Okay, I'm going to scribble it out. And I'm going to flip it, so that means I need to change the sign. And so 2H2O gives me 2H2 plus O2. Okay, so now my waters can cancel. And these cancel out my hydrogen, that's good. And I'm losing an oxygen. So this cancels, and this will go to 5. I can cancel out 1. So let's rewrite those. So let's see, I've got this still, and this still. So 2N2 plus 5O2 gives me 2N2O5. Okay, so that matches the equation here. So now I can just add up all these heats of reaction. And that gives me, my delta H is 22.6 kilojoules per mole is your units for this. Don't freak out. We will practice these. Okay. All right, so here's a bit of a quicker way to do enthalpy. So it's the change in enthalpy, right? So it's your final minus initial. Well, for chemical equations, your final is your products and your initial is your reactants. So what you're going to do is you're going to look up the delta H, the heat of formation, on a chart. You'll always have a chart. The only thing that won't be on your chart is if it's an elemental state. It'll always be 0. So our equation is balanced, and we're going to take our products and we're going to subtract our reactants. So I have CO2 plus 2 waters, and these are gaseous water. Okay, you need to start paying attention to your states of matter. I'm going to subtract my reactants. I have a CH4 plus 2O2. Okay, now I'm just going to look these up on the table, plug them in. So CO2, negative 394, plus 2 gas waters, that's here, negative 242, negative, minus methane, let's see, is negative 75, plus 2 oxygens. Oxygen is diatomic. That means it's in its elemental form, so it's 0. All right, and when I plug this into the calculator, I get negative 803 kilojoules per mole. All right, try these and we'll check your answers in class.